I will actually.
Okay. Hello, good morning, everyone. My name is Naresh Sehgal, and I'm here with Professor Bhatt to present a brief overview of 2 chapters from our book. There is a link on the front page at the bottom where you can go and look at Amazon. And I think with the Kindle app, you can get a preview of something like 30-40 pages of the book for no cost. So Kindle and Google allow you to do that. On page 2, we have a layout of the different chapters. So there are 14 chapters in the book, and we picked up 2 chapters based on folks I talked to and what they wanted to hear. So this is really, one is a foundation, how cloud computing came about, and the other one is where it is going, right? And everything else is in between that we are not covering today, but if there's a need for any particular thing, I'll be glad to come back and cover. And at the bottom, we list specific appendices. So at the end of each chapter, in form of a very light exercise, we have some questions for folks to think or points to ponder. And then there are some additional consideration on Appendix B. And then Appendix C has some lists of projects if people want to do more hands-on work. There's already a list of quite detailed projects in Chapter 14. So I will go to slide number 3 now. So, with Professor Bhatt's long time experience, he taught at IIT Delhi for almost 30 years in computer science department. He retired as the head of the department there. So he made me see the light of some sort of a pendulum or, back and forth which is happening in computing, where on one side of the pendulum you have computing in a centralized place like mainframe used to be, and on the other side you have dumb terminals and they're connected through pipes, right? And on the other side you had very powerful workstations or PCs, which for a while can be very good, very powerful standalone machine, and only if need be they are connected in the back. But instead of depicting this as a pendulum going back and forth, we thought a spiral would be a good way. So we start with mainframe, where the computing resides in a central place, and this was in 50s and 60s with IBM mainframes, and people will be sitting in front of terminals. Go ahead. Is there a comment or question? Okay. So from there, the next thing that came was actually mini computers, but we sort of skipped that because that is a mainframe shrinking into mini computers, like from IBM 360 or DEC 2050 type of a mainframe going into VAX 11780, which would be a mini computer. And then PCs came, where of course Intel was fortunate that it got picked up. Its microprocessor 8080 got picked up by IBM, and then Intel became very big with that. And then workstations. So what you see with PCs and workstations is where power is more closer to the user as opposed to be somewhere far away. And then at the top of the curve is again client-server computing. And the reason it is a spiral and not a pendulum going back and forth is that the amplitude of pendulum is increasing, or the spiral is growing bigger with each turn of going back and forth. So when you go from central power to edge power, you get more people in it. So with client-server computing, again, you had clients as well as servers. So both are very powerful. There was more sharing happening. And then from there, it evolved, and now the clients are no longer PCs or computers or America Online that you got mail kind of things, but these are smart devices. These could be tablets, smartphones, or devices in hands of people, and they became very powerful in their own right. For example, if you are holding a smartphone, you have more computing power than the Apollo 11 rocket had, which took men to moon and brought them back, right? So imagine the amount of power you have, and the knowledge that you can get by connecting to internet on the back is more than President Ronald Reagan or President Clinton had in terms of the knowledge base. So you can sit and ask any questions about any part of the world, and you can get answers. And before that, people had to go to CIA and libraries and so on and so forth. So internet has become a big research tool. So again, smartphone spiral is very big because a lot of people have. You literally have a few billions of these devices, but connected to spread out servers. It's a very, very huge, vast network of knowledge. And you might have seen data, and I will show that every day there's enough content created equivalent to what was created in the last 50 or 100 years. So the acceleration is very huge, right? If you see the hockey stick curve, where with time how much knowledge is being created and content is created. Of course, you can debate what the worth of that is, but still people are uploading a lot of photos, sharing a lot of things with social media, etc. And mobile apps that I talked about with cloud computing can do wonders, right? Sitting here, I can pay my bills in India. I can help relatives. I can reach out to people almost instantly. And companies ran into a problem at some point because they felt that the sale of new machine was slowing down after the mobile apps and smartphones. Everyone had one. And the only sale company was able to do, even Apple or Android phones, was when people will replace or upgrade their phone, which will be every 1 or 2 or 3 years at a time. And number of people in the world is limited, right? It's about 7.5 billion people. So how do you sell more devices? So then folks came up with the idea of Internet of Things, where you can go to something as simple as a light bulb and give it an IP address, and remotely you can turn the light bulb on and off by talking to that IP address. And that has a lot of power. Think of a building with energy management where, if nobody's sitting in a part of cafeteria, why should there be a light? Why should the air conditioning vent be on? So by having all these devices and sensors to see who is there, who is not there, you can turn things on and off. So combination of Internet of Things and cloud computing is very, very powerful. And what is happening next, and we'll talk more at the end, is edge computing with local intelligence. So you see that the spiral is growing, and again, with mobile apps, with cloud computing, the power was more on the back end, right? When you play Netflix movie, you're only using a display device. Movie is actually being decoded or encoded in the back. But with edge computing, again, the pendulum came, more power and more memory and more compute on the devices. So this is how things are going back and forth. So any questions on this slide? All right. So we are on the next slide, where I would invite my co-author, Professor Bhatt, to talk about service-oriented architecture. So go ahead, Professor Bhatt.
Yeah, thanks, Naresh. I think we are on slide number 4, just in case somebody is managing the slides. So to begin with, good morning and greetings from Bangalore to people who are from outside of India. And well, let me try and explore this particular foil which you see in front of you. But before I do that, let me try to give you a little brief on how we may interpret this particular foil. This is more about service-oriented architecture. However, I would like to begin by saying that almost anything that you do, in fact, is a part of the total software architecture regime, and software architecture could be contemplated more in the nature of a plan or a blueprint leading to a solution. So emphasis is on the word ultimately getting a solution. And to that extent, software-oriented architecture is a form of software architecture, which essentially is a solutions architecture. I think I could probably best illustrate it with some kind of a small example, which I'm sure you can quite easily relate to. For instance, you can think of an airline's reservation service system. Basically, it's a service. And what you have is some form of a presentation layer which opens up the portal for you. And there's a customer interface, which of course where you fill in some details or queries or whatever. And then this must interact with the business layer. Why I say business layer is because depending upon what you are querying or what you are entering for booking, you may actually also be led to a payment procedure, or you may be led to just querying and interrogation to a database. So at the end of the day, you may be actually interacting with the airlines database, or you may be interacting with another broker who may be offering you, like Make My Trip, who may be offering you multiple kind of options, and then internally they interact with the airlines databases. Now, if you think in terms of you as a user, the reservation system as a service, payment procedures as a enterprise with the bank in the background, and airlines itself as another service or a database layer, then what you see is that there is a cross-enterprise interaction happening. The primary motivation for a service-oriented architecture comes from the fact that at the end of the day, you're looking for a cross-enterprise solution. Now, where does the pain point begin in this situation? The pain point begins with the fact that the data in this particular context or in any other cross-enterprise solution context and the functionalities. So data and functionalities, they are residing in different systems. When I say different systems, this could also mean using different platforms, different forms of interfaces, and so on and so forth. And here, the immediate problem is the extent of tight coupling that exists in the internal systems vis-a-vis the external communications. So, all this background I'm giving to suggest that applications need to be able to communicate and seek specific forms of services. The point is that in an airline's reservation system, or for that matter any other service-oriented system, there is a need for an application to be able to be usable in some very specific context and obtain a specific kind of service. Now you may recall that one of the things that the software architects and designers contemplated at one point in time, specifically trying to get the Microsoft into the in the picture of being able to have interoperability, was a system called Corba, which was basically a brokering system, and the .NET framework subsequently evolved. Now you may say that did offer a certain extent of interoperability, and brokering did help in communicating the objects across different functionalities that were available. Since we are talking in terms of the enterprise solutions, one would look for something which offers, at the end of the day, an extent of open interoperability. So the emphasis now is essentially enterprises ought to be able to communicate with a degree of open interoperable systems. Now this infrastructure obviously is the internet and the web, and the need to be able to have interoperable system required that there be service interaction protocols. These service interaction protocols are what one would look for. Now coming back to the foil, if you see right at the top is a box called SOA, and if you trace a path to the next layer, there is a box called service, and then there is a box below it called implementation, and below that is what you see data and business logic. So I'm tracing a path on this particular service-oriented architecture description, where I'm saying that at the end of the day, there is a particular service, which is what we have been talking about, which is driven by the particular application seeking the service, and there is an implementation which brings about a communication with the data and business logic. Now the point that I am trying to make here is data, business logics could be residing on different platforms, different systems, on different enterprises, and these need to be able to communicate. So the kind of technologies that made this possible, which are called the core SOA technologies, are essentially the use of the XML, the SOAP, which was the Simple Object Access Protocol, the Web Services Description Language, WSDL, UDDI, which is the Universal Description and Discovery and Integration, and Enterprise Service Bus. Now, in the book, you will find that beyond this diagram, which is appearing on the foil, there is description for how to capture the underlying technologies that I mentioned just now, and the advantage. Now, let me try and indicate the primary motivation for SOA by way of indicating the advantage. See, the disadvantage was the tight coupling between data and functionality. Now, what the SOA does is to immediately open up for interoperability with loose coupling. So the emphasis is on loose coupling, and this comes from a variety of enabling technologies or utilities, if I may put it that way. One is, of course, network transparency, which goes without saying, but the other very important one is the virtualized endpoints, the self-describing software, because with UDDI it is possible for you to have discovery of the services. So there is the universally describable, discoverable, and understandable description of the software. And then this enables the machine-to-machine communication, which actually means that it's possible to now have the cross-enterprise solution, which is more in the nature of loosely coupled services which are integrated into an architecture to offer a particular or a set of solutions. So this may, coming back to the foil in our front, you notice that SOA for a particular service, if you look at the second layer, will have service repository and an application front end. And obviously it operates through what is called the service bus, and so on and so forth. So as I said, this particular foil essentially was to capture the essence of the service-oriented architecture. Now, let me just check if I have been too rapid in my explanation or fast, or do you have any questions at this point in time? Then I will move to the next foil.
Yeah, I think no questions.
Hey, I do have one. Sorry, maybe I missed.
Yeah, go ahead. What's the question?
Yeah. Hey, what is service bus? Can you explain a little more? I think everything else, it makes sense to me. The service bus is like a group of services, or how do we visualize that?
Well, to visualize service bus, you ought to essentially think in terms of channels, essentially a channel that allows you to be able to have communication between two ends, and the channel could be shared. The notion of a bus is essentially to be able to have a shared path, to be able to have a kind of a communication, if I may say so, and be able to have between the enterprises have a set of, let's say, between a service which requires a specific kind of response and another service which requires a different kind of a response. Both could be sharing this channel through a service bus. One could be related to accounting, the other could be related to stores and management. I mean, in a typical enterprise context, that is what it would ultimately support. So that is what is meant by having a service bus. But
so if I can look
I hope
that
I've
way,
been able to.
sorry.
Sure.
No, sorry. So I can look at that. We have one service as a process, but can use that to apply to different use cases.
Absolutely. Well, I think you put it succinctly. Yeah, you in fact put it much better than I did. Yeah.
No. Thank you.
No. The fact is a fact.
So should we go to the next file, sir?
Yeah. Okay. We could probably move to the next file then.
Okay.
Now, this is where, I want to bring out something which, in the enterprise community, we use a phrase which is called CTQ of any process. CTQ largely relates to cost, time, and quality. And what this foil actually shows or depicts is the CTQ of a SOA vis-a-vis the traditional approach. So if you carefully notice, or from the description that I gave you for the previous foil, there are one or two points which I like to again go back to and emphasize. If you recall, what I did say was that it is a cross-enterprise solution. B, it is an end-to-end solution. And C, actually it is very agile. Agile in the sense that if there is a new business process being developed or incorporated, it would be relatively easy to operate it at a particular layer, because there is a layer which you may consider as a service layer, and there is a layer which you may consider as a resource layer. The database is a resource layer. There are certain layers where you may have, for instance, a presentation layer is partially a service layer and partially a process trigger level. Then there is a layer which usually the services really operate with, which is called process orchestration layer. Now, in the process orchestration layer, usually you initiate and trigger the processes. Now, the reason why I use the notion of agility here is that either in access or in orchestration or in the service or in the resource management, if you really bring in a new methodology, it is relatively easy to operate, because much of it is operated as a layered architecture. Let me give you an analogy here. An analogy would be that on the internet, we invariably use the TCP/IP protocol, and we have what you may call as a layered architecture. Now, had it not been for the layered architecture, just imagine the kind of pain we would have gone through in moving from IP version 4 to IP version 6. The fact that it was a layered architecture, I'm not even remotely suggesting that this actually was very easy. But what I'm trying to say here is that the vendors, the companies, and the protocol providers had to work at a specific layer without impacting the TCP part of it. That is what I'm trying to say. Okay, so in the same manner, in the SOA, one of the things that does happen is that the SOA's access layer or process orchestration layer or service layer or resource layer can be independently altered. That is, if there is a database which is operating with an archaic Oracle, let's say version 7, and now the company decides or enterprise decides to move to 9 or 10 or whatever, then it is relatively a less painful task to be able to incorporate that. And that is what basically is indicated in what is shown as a cumulative cost on the y-axis and the capabilities implemented on the x-axis. So you see, SOA flattens out in terms of the cumulative cost as opposed to traditional approach, where a lot of what I may consider as a tightly coupled system will have to be unlocked, destructured, and then bring in new capabilities with new kind of APIs, and even have to probably, it just won't work. So precisely the point that I'm trying to emphasize here is the SOA, with all its layers that I mentioned or talked about, offers what is called the CTQ benefits: cost, time, and quality. The CTQ is an essential measure of an enterprise's ability to be able to operate with service orientation and, as I said, offer cross-enterprise operations. I suppose that is what this particular foil, I'm emphasizing that this is what this particular foil actually offers you. Now, do you have any questions on this or the manner in which you may wish to comment or make observations? Any of the participants may want to wish, or Naresh might want to add something.
I think maybe you can tell us what you told me, how we jumped from SOA to cloud, and then we can go into the next.
Yeah, I think in between I got a signal that somebody probably is asking a question. So let me take the question first.
Okay.
Is there a question on the bridge?
I did get.
Yeah. So I think
I think there was a.
Yeah. Somebody joined, I guess.
Was it
Yeah. So no problem.
Yeah. Yeah. No, I did hear some human voice. That's why.
Sometimes
anyway.
There could be some ambient noise. Yeah. So no question.
Yes. Yeah. Okay. Now I think Naresh has specifically asked me this particular point to be emphasized, where having said that, the service-oriented architecture is essentially a cross-enterprise service solutions architecture. Having said that, if you look at it carefully, there were a few points which I attempted to emphasize here. One was the fact that there is a large number of what you call as databases, which obviously are in what is called a resource layer. In the resource layer, there will be implementations which are more in the nature of Oracle databases or some other databases, or in the context of a operator using, let's say, the IBM, there could be WebSphere-based service layer which could probably be implemented. Now, the short point is that where do these reside? They reside essentially either on a server farm or graduating from the server farm into a cloud. The cloud also affords you, relatively speaking, an interesting facet of the access layer, and cloud can also be very effectively utilized for what I call as a process orchestration layer. Now let me elaborate a little bit on this. Cloud enables you to be able to decide on workload distribution, and a process orchestration, depending upon the nature of activity at that particular point in time, will help you to be able to execute whatever processes there might be with a deployment on a cloud by distributing the workload. So I think this is relatively easier as opposed to when the services are, let us say, monolithically or singularly operated with a fixed kind of a configuration. That is why the cloud makes it relatively more acceptable or the SOA ultimately graduates to a cloud-based operation to facilitate the access, process orchestration, and management of the resource layer. So, Naresh, have I indicated?
I think you have made the link beautifully. Yes, yeah. And now I can go to the next file. Yeah, I think you made the link beautifully.
Yeah, just let's check if there are any questions before you do that.
Are there any questions for Professor Bhatt on the last two files? Okay, I take that as a no. So, sir, please continue to stay with us, and there will be more questions later on.
Yeah, all right, fair enough.
So I'm on the next slide, cloud computing according to NIST. So, as you heard, right, so there were mainframes, and, there people were using virtualization since 1960s, and actually in IBM 360, the term was called virtual machines, because each user's job was separated, memory and programs and data was separated from the other user, so they were partitioned, and every user was made to think that he or she had full machine, but actually it was doing time slicing. So there were mainframes, then there was a grid computing, there were pools of computers with client server computing, etc. And whosoever came up with cloud computing term, this is a beautiful marketing term actually, because it somehow says that my data is in the cloud. That means you do not know which machine it is on, which location it is on. An example would be Gmail, right? So I'm in US, so I open a Gmail account here with Google in Mountain View, but I'm flying to India, and when I land in, let's say, London or Germany to change my flight, I can walk up to a web browser in an airport and open up, and I can access my Gmail there, right? And when I reach India, I can do that also. So what Google has essentially done is they have given me access everywhere, right? So that is a ubiquitous point of it. So it is there, always there, 24/7, anytime I want it. It is very convenient. I don't have to be in a particular PC or a laptop or a particular machine. I can access it, my service from a laptop anywhere where I have a web browser or a smartphone access. And it's on demand, right, whenever I want it. And on the other side, you have a shared pool of configurable resources. By computing resources, I mean a collection of networks, server, storage, application, and services. And Intel IT with NetBatch sort of does that, right? That you may have an idea that your job is running in a particular data center in Oregon or India or somewhere else, but you do not know which rack of server or which machine your jobs are on. And some time ago, IT started doing mirroring, so your data would be mirrored across different data centers, so your jobs could migrate wherever the compute capacity is available, because otherwise you have a wait of few hours to run a NetBatch job on one machine. On the other side, the utilization is low. So that way you can very rapidly bring systems up, very rapidly provision them, and also release them. And the idea here is a self-service, right? So you don't have an IT manager in between where you're ordering something, because I can tell you an example on a project in Intel about 10 years ago at Jaketown, where they wanted a few terabyte of disk. They had to place an order. They had to wait 14 days for it to be arriving and configured and make it available. So the work would be slowed down or stopped in between. But with cloud computing, whether inside or outside, anytime you want something, you can theoretically think of infinite pool of resources. And the most beautiful thing is that you pay on demand. So it's like electricity or like water. You open the tap, the water comes out. So computing becomes like a utility, and you're only charged for what you use, right? So that is the whole idea of cloud computing. And NIST is an American body, National Institute of Standards and Technology, which gave this rather mouthful of definition, but I try to give you an idea of what cloud is. And it started with 3 layers of service. So at the bottom is infrastructure as a service. So you get a server, essentially, or equivalent of a server. Now, this may not be full physical server. If you're going to Amazon, you could be sharing a server using VMs. If you go to Google, you may be sharing the server using containers with Kubernetes. So different people will use different methods to do sharing. And the reason they do sharing is it cut down their cost, right? The difference is like sharing, an airplane seat with other passengers. Airplane with different passengers, each one having their own seat. But the cost gets divided, as opposed to maintaining your own Boeing 747 to fly from, one place to another place. Very, very expensive. So with a server being shared, you could be paying as little as a few cents per hour. But you get a bare bones server, right? And you can say, I want a Windows server or Linux server, but that's all you get. The next layer service that is built on that platform as a service. So there you can get some other services like a Mongo database or SQL database or some other kind of software stack that you want. So you get a platform with the installed, and you don't have to worry about versioning and making sure latest patches are there, because the cloud provider makes sure you have all those things. So that is PaaS. The next layer up is where they give you a particular software as a service, where you do not care about where that software is installed or which operating system it is running on. So you don't care about the hardware, etc. An example of this is a company called Salesforce. So Salesforce.com provides a tool called CRM, which is the customer relation management database. If you were going with Oracle or another company in the past called Siebel, you would be buying very expensive software, installing it. But with Salesforce.com, your service is hosted in Amazon Cloud, and you're only paying for what you use. Another example of Amazon service is Netflix, where instead of buying a DVD and having a player or buying a cassette or movie yourself, you are basically paying for a service. In US, it's less than $10, $7 or $8 for unlimited movies you can watch on 2 TV screens at any given time, and you can watch it all day and night if you have time. And they don't charge you per movie, and you get streaming service. And you don't own the movie; you're just using it for the moment. So that is the idea of these 3 services. Now there are other forms of things which are coming up, and we talk in the book in the appendix. So one is called FaaS, Function as a Service, and AWS has a service called Lambda, where instead of having a server that you're renting for an hour or a service that you're subscribing on a monthly basis like Netflix or some music service like Spotify, in a function as a service, when you need to do something, it invokes a method, and the method runs for a few milliseconds. For example, you're doing a search on a database, you're looking for some flights or some other service you want. When you click the button, only then it will provision the resources, it will run your job, and then it will go away. The resources will go away to someone else, but you only pay for those few seconds. So that is called function as a service. So like that, there are other things which are coming up, but these are the 3 basic layers. And the type of cloud where people are provisioning this utility computing are public clouds. So an example would be Amazon, Google, and Microsoft Azure. So these are the 3 large players in US. Amazon is the largest. They are about half of public cloud in US. And actually, after that, second one is Microsoft Azure, although these things can change. And the third one I thought was Google, but actually it is Alibaba in China. And then Google with a very single-digit 3 or 4% of the total workload. So half of it is Amazon. So that is an example of public cloud. A private cloud is, for example, what Intel IT offers with NetBatch to its customers, where customers don't necessarily know which machine their data is running on. Their machines may even get shared. When one guy is not using the machine, someone else can use it. And I'm not sure these days how charging is happening. Are people paying for the jobs being run, or do they still have to pay some for the machines? But a private cloud is where an enterprise owns the cloud inside a firewall. A hybrid is a mix of public and private. So Microsoft Azure has a system where they call it Azure Stack, where they place one or more servers on your premise. So think if you're a lawyer or an accountant and you don't want to depend on public internet, the reliability is weak in some countries. So you will have a data on premise, and you're hosting it there, and only the backup and disaster recovery is happening in the background. So even if the internet connection is cut to the outside world, you can still do your accounting job or your legal work. And once in a while, the backups are taken, or when jobs become big, then they go and run in the public cloud. And that model is called burst computing, where you burst out of a private to go and run into the public when the load is high. So are there any questions on this slide?
Just one question, Naresh. Maybe you may be covering this, but from the security point of view, I would guess private is the most robust, right? Or you think public cloud? Some, yeah. Mm-hmm.
So I think security has many different angles, and when the data is in your control, we feel better about it, right? And I would like to give you an analogy. In the old days, both in India and in America, people used to keep their money at home, under the mattress or in the home. And I personally suffered a home robbery in US where we lost a lot of things, right? So my wife's whole jewelry, everything was gone. And then I went and started putting things in a locker, right? But if you have, and people were not putting money in the bank in the old days, 100 years ago, even in US, thinking that bank will fail, right? Because there is no indemnification. So I think of cloud being like that in the early stages, people feel more comfortable when they can see where their data is and it's under their control and they're paying a price for it. But I can tell you, I went to Amazon in Seattle with the same question, and the guy showed me the level of controls they have before someone can walk into their data center are very, very high. And even the operators there do not have access to the data. There's no USB keys. There is nothing they can physically steal. So, it's a question of economics, actually, right? Because CIA, which has a lot of confidential data, as you might imagine, is using Amazon public cloud. And within that, they have VPC, which is a virtual public cloud. So basically, they have taken some dedicated servers, which are on a separate network, but within the Amazon management. But other users' jobs are not running on those machines, right? So they're isolated. LAPD, Los Angeles Police Department, is hosting all their records in Amazon Cloud. Boeing is doing their aircraft design using Amazon Cloud. So, those organizations are very security conscious. So I understand, Intel at this point chooses to keep all the design data in-house. But we have migrated, our employees' salary information, at least in US, a lot of healthcare data, a lot of hiring and that kind of stuff. So Workday. And Workday is nothing but a cloud, right? It is not really a public cloud, but it is available to many companies. A lot of companies are using, NVIDIA is using Workday. So what is the guarantee that Intel and NVIDIA jobs are not sharing the same physical infrastructure? We don't know, right? Mm-hmm. That's the whole idea of cloud. So I think slowly people will become comfortable.
I see.
But I think the reason design data will still take time to migrate, and we have a full chapter in the book on that, is that EDA needs not just companies like Intel to feel comfortable with our design data, but the EDA companies have to place their tools in the cloud, right? So today those tools are licensed, only to the companies that are using them.
Right.
So I think the way things are today at Intel, the way I understand is all our design data is housed inside, but pretty much everything else, right, all the employee data, all the payroll data, HR is in Workday, which is outside.
Mm-hmm. Okay.
So I think you know which way the trend is going, and economics is what's driving this trend. Right. So I hope I answered your question.
Yes, thank you.
Yeah. So people who are experts in cloud, is there another question?
Yeah. So, based on you mentioned about 3 different kinds of services, right? Cloud services. I also heard about the data center as a service. Can you briefly talk about how different it is from the platform as a service?
Yes, sure. Yeah. So companies like Internap, which is right across Intel's R&B office in Santa Clara, are giving you hosting services. So they are giving you a cage where you can go and place your own server. And they give you the power, and they give you equivalent of an Ethernet connection and air conditioning. And they're basically physically looking after your server to make sure that it is secure in a lock, and it is cool, it's running, getting the power properly. But it is your own server, and a company called Sony is using it. So when you play a Sony PS4 workstation game, right, when you're playing with other players, that game is being hosted in Internap. So they are giving a hosting service. And, it's known as various names, but I think that's what they mean as a data center as a service. And now there's something else called DAS, data as a service, which is different than data center as a service, right? Data center is more infrastructural. Data as a service is more like where somebody is collecting a lot of data and they are giving that as a service. So, for example, on Amazon, there is a lot of genome data which is available. So as a medical researcher, if you want to do some drug trials, instead of doing that on live humans, or you want to look for some disease patterns, they have collected this data which is anonymized. So you don't know the name of patients and people and all that. You know their demographics, you know the age of a person and, you know, maybe their race, etc. But you can use different kind of data. So companies, you know, for example, when they're training their automobile self-driving cars, so they are using a lot of data like that, right? So different companies offer data as a service with different kinds of data. Did I answer your question?
Yeah, very well. Thank you.
Okay. So in the interest of time, I think next slide content, we already talked about what is happening. So, you know, people are migrating to cloud, not only for individuals doing the Gmail as I talked about, because that's what Google and, you know, other companies start offering it as a free service to run your search engine, to host your mail, and Facebook is hosting your photographs to share with your relatives and friends. But actually businesses are going, and that's the next slide, Professor Bhatt, saying business services using cloud. And this is where SOA migrated, where you have network infrastructure as a backbone. And this is both the network connecting you to the data center and the network within the data center. They're collecting all the storage and all the servers together. And then using virtualization to share resources so that CPU storage, etc., is split among many people. So the cost is divided. And you know, basically it's like sharing seats on an airplane, and each person only pays few hundred or a couple of $1,000s, and you can pretty much go from any point A to B in the world for you know, less than $2,000. But if you see the aircraft cost and you know, which is in tens of millions of dollars, and the fuel and all that gets shared. Same model is used here. And the data center operator takes care of control and administration and monitoring. And then they offer some web services that Professor Bhatt talked about. And in the book, we have a separate chapter on the service level agreements which are there. And today in the cloud, I can tell you they are very, very weak, right? They do not guarantee you certain bandwidth, or they do not guarantee you some equivalent of a CPU capacity. They will just tell you you will get equivalent of a Xeon 2 gigahertz, but they don't tell you which generation of computer. And actually in a data center, they have 3 or 4 generations of machines, because whenever Intel launches a new server, they don't throw away their old ones. They only replace 10 or 20%. So over 4 or 5 generations, they have a mix of different machines with capabilities. So when your job comes, you know, you don't know which machine it lands up on. And then they take care of billing, and there are other different policies they have on what you can or cannot do. For example, Facebook, I was reading yesterday, suspended about 100 applications which they felt was violating their policy with the user data. And on application versioning, again, the cloud operator takes care of it. And about Facebook, I'm sure many of you use it, but you may not know that Facebook is a monolithic application. It is rebuilt every night. So every night they roll out in a very agile way a new version of Facebook application, but they don't roll it out to all, 2 billion users. They only roll it out in some segments. They try it out. If it doesn't work, they roll it back. But over time, it's like a wavefront. It goes to different people. But, when some new patches came, for example, there were some bugs before and there were patches were rolled out. So AWS and Google and these guys were able to install their patches pretty much on running machines, right? And you don't have to worry about making sure that you're running the latest version of OS. Whereas on a PC, I have to worry about, do I have the right patch or not? And then there's a retail interface where, different people, developers, service providers, people who are publishing content, they can go and interface with that, right? And in the book, we go into a lot of details. Now, I want to look at both sides of the coin. I'm on the next slide titled Benefits and Limitations of Cloud Computing. So benefit is very, very obvious, right? It's all driven by economics. So if you have to buy a server, it'll cost you $2,000 to $3,000, and your total cost of ownership or TCO will be equal to or more than that. That means if you take into account the cost of software, cost of hosting that server, power, air conditioning, etc., and cost of software, cost of IT people to manage it, And basically, by sharing it, by moving it in a central place, you share all that cost. So cost is number one seller, and this is the reason companies like Boeing or CIA or LAPD have moved. Even Disney is fully in cloud, and they are in IBM cloud, by the way. Second one is pay as you go. So you don't have to make upfront investment, and you only pretty much pay for what you use. And this one is a big deal, on-demand elasticity, right? The example I gave you of Jaketown project, when they wanted more hard drive, they had to wait for 2 weeks to order it from NetApp and get it and install it. So there is a large pool of available resources you can draw from that on demand and release them. And the focus is on application layer, and let someone else worry about the hardware. So a lot of companies have started in US, Airbnb, Uber. A lot of these companies are serving flowers.com and other services where they are only focused on their customers and what value they are providing and not worrying about the back end or hardware. The limitation is data movement, because in the public cloud, even today, you have a vendor lock-in. So when you go into Amazon, imagine if Facebook started, if Mark Zuckerberg started in AWS, when his company grew big, there was almost no way he could get out of it. He will be locked in. Why? Because Amazon uses something called AMI, Amazon Machine Image, and they have their own proprietary database, right? They were using Zen, now they are using something else for their VMM, and you don't even know that, right? Because everything is hidden. Google uses their own different proprietary operating system and Kubernetes version. So it's very easy to go in a cloud, and if you expand your business, it's very hard to migrate from one public cloud to another public cloud. That problem is still not solved. The second one is loss of control. So you don't have full control on your data. So there are laws being put right now. There's a HIPAA law in US for healthcare where the data cannot leave, for the patient's US boundaries. So you cannot have data hosted in other countries. GDPR is a new law in Europe which is coming up on saying which data are you collecting and how you are using it. And other countries will also see and put this kind of a law to protect its citizens' information. And cloud security, right now I call it a perception, because the biggest incidents that we had on security breaches, they are not on public clouds yet, right? So Equifax was a big breach where I think 45 million or maybe 145 million people worth of social security numbers were stolen because Apache server did not have the right patch installed in a known bug. So I think if you look at the public literature on computer security or server security, a lot of breaches have happened either because of insiders, some disgruntled employees or somebody insider job, or somehow somebody was able to breach the firewall. But all of these incidents happened in private clouds, not in public cloud. Right? So right now, the large public cloud operators say this is a red herring. It's not real. Now the last one, what I want to talk about is uncertain performance. This is a big issue which no one is really talking about, right? So this is the elephant in the room. So when I taught this class at Santa Clara University, I had my students run their job for 24 hours a day, different students, and we had a tool which we were using, which was simply measuring the CPU performance, the storage performance, and memory performance. And the way we were doing was we were simply executing instructions like read-write from memory, and we were flushing to make sure it's not cached. We were opening a file, closing a file very rapidly and doing it in a loop millions of times. And we were doing CPU instructions like some floating point arithmetic in a loop again million times. And we were benchmarking that. And we saw the performance variation. And you can see that performance variation is not nearly 70-80% over time, right? At different hours of the day. And the reason this was happening was the students in the class or the customers of cloud had the same machine. Their jobs were not migrating, but AWS was putting other job on the same server. And on a server, when you have multiple CPU cores, you can give different core to different jobs, but still there are a lot of shared resources. You can also partition memory, but the interface to read and write for a SATA drive or Ethernet port, all those things are shared, right? And that's where the bottlenecks happen. And that's why you see the job will suddenly slow down or speed up depending on who else is using that. and this is a problem. And I can go into more detail here, but I'll tell you that company like Netflix, which has to encode movies, and MPEG encoding is a very compute-intensive process. They spend a lot of time trying to figure out or do reverse engineering of which architecture or which version of Intel CPU their jobs are running on, and if they have an old one, then they reject that VM and they request another one, until they get a fast machine, and they keep it for months, because the speed up of a new machine versus an old machine is 2 or 3x, right? But we did not have any such luxury. So we, in the class, the students, when they were running those different benchmarks in the cloud, they ran it over time and averaged it over a quarter with different students. So we saw a lot of variation, right, in the different scores. And the total variation was about 100%. And we have these charts in the book. So then I had students try out different clouds. And I did not give the name in the book because I didn't want to invite any lawsuits. But I can tell you here, the vendor A is Amazon, M is Microsoft, vendor D is DigitalOcean, G is Google, R is Rackscale, and V is VMware. So I had different groups of students try different cloud servers. The largest variation we saw at that time was in Microsoft. And I think the reason Microsoft had largest variation was because they were hosting Linux jobs in Hyper-V on a Windows server. So you had 2 layers of OS. So every time you want to open a file or close a file or do some operation, it has to go through multiple layers of data. And it was very sensitive to performance with who else was running. Then we also went and tried with different hypervisors. And Hyper-V we found to be the worst in coefficient of variation. And the Linux KVM was next one. And OpenStack did pretty good, right? And we did not know what DigitalOcean was using, and vCloud was very low, right? They had the best control on ESX. Now, the last chart on the right-hand side on this performance is very, very interesting because, students had their jobs running like a cron job, which will wake up every minute and it'll run this performance benchmark, log the data, go back to sleep. And it was running literally 24/7, and we collected a lot of data and did data mining on it. And I used to think that cloud, a public cloud like AWS, will be very slow on the weekends because no one is using it. But what I found was that weekend usage was very high, so the variation was highest. And cloud was relatively not busy on Thursday and Friday. And I think the only thing I can think this is happening is because everyone wants to go home on Friday and not bother about work. So basically they run all their jobs or the reports or accounting or engineering or whatever work you're doing. You run it till Wednesday. On Thursday, you sort of look at the data, the log files, and analyze. And Friday, you prepare the reports, and you submit your weekly report to your manager. And then you submit new jobs and go home on Saturday, Sunday. So if I don't have a lot of money, if I'm a startup, I will run my jobs on Thursday and Friday because then I get more compute for my money, right? My jobs will run very fast because not many other people are there. So if you go to a public cloud, don't just think you'll get the same performance all the time, right? That's the lesson from this slide. Any questions on this slide? All right.
Just a comment. So the user experience also is directly proportional, right, to the performance. So for this, the use case like Netflix, how do they guarantee the same user experience?
So Netflix, what they do is they use edge computing. So they work with Akamai and they place some servers close to your home in the neighborhoods. So instead of serving you a movie out of Seattle to Santa Clara, California, which is hundreds of miles away on the network, because this is how they were doing a few years ago. And I actually canceled my Netflix service because movie will run fine on all other days, but on Friday evening when I sat down with my wife and children to watch a movie, in the middle of the movie I get this circle saying waiting or loading. So you literally had a James Bond chase going on with a car stuck in the air and the action scene stopped fetching or buffering more data. And it really ruined the whole fun of watching movies. So I called Netflix guys, and they blamed it on my router, or they said my firewall is a problem. I said, I'm not going to remove my firewall. So I realized the problem is in my neighborhood, everyone is watching a movie on Friday evening. That's why it's slow, right? So I think they learned something from it. So instead of having, a dumbbell kind of approach where all the computing is in a faraway data center and all the clients are on the other end with a pipe connecting for data flow, they created this islands of compute close to where you are, and they do a lot of caching or buffering, and they call it edge servers, right? And Akamai is an expert in providing that service. So, for example, popular movies are stored very close to where you are located.
I see. Okay.
Okay, so internet has really grown, and since we finished writing book at the end of last year, this is the data. I'm sure things have even become more busy now. So this is just giving you, for example, in Uber, which does not own any cars, right? It's a ride-sharing service, Uber, and I think in India there's Ola. So they are taking something like, 4.5 million rides per day, right? On Spotify. So this is just happening in every minute. What is happening? Sorry. So 4.5 million in every minute of a day, averaged over whole 2017. So many rides are being taken, right? On Spotify, in every minute on the internet, 30 new songs are being played. And Cisco looked at the data that is flowing on its network, the video that is flowing. The video is taking a lot of data. If you take 1 minute of video flowing across the internet, and you as a human being want to watch that video, it will take you 5 years of your life to watch the amount of video flowing in 1 minute on internet, day and night, 24/7 for 5 years. That's how many data is flowing. And in 1 minute, for example, Google is conducting 2.6 million searches. So like that, there is some other data, or Amazon is able to earn about $300,000 in sales every minute, and that's why their stock is doing very well. And Netflix in 1 minute is sending nearly 70,000 hours worth of video. And you can calculate how many years it will take to watch someone, right? So internet has grown beyond the wildest dream. It's probably one of the biggest inventions of the either end of last century, but it really started long time ago, of course, with DARPA project, and we touch on that in the book also. Now the next revolution that came is IoT, or Internet of Things, because they figured out if it's only people watching video or people taking Uber rides or listening to songs, there is a limit to human beings. You have limited number of people in the world, right? So you're going to run out of the applications that you can sell because you're competing for the same human time. So people then move to device kind of models, where I gave the example of a building with temperature sensor controls, and you are doing energy management, and even in your refrigerator you could have cameras. So you're out shopping, you don't know whether your milk has finished or not, so you could turn on your app, you could find out that what is the expiration date on your milk, you have half gallon left, should you buy new or not. Otherwise sometimes you come back thinking, oh, maybe I should have gotten my eggs or some vegetables or not. So there are all these devices which are opening up, and I think security is a big risk here, so we talk about that. So more than public cloud, Sharmila, the question you asked, I think in IoT, security is a big, big issue. So this is a very growing area. And we explained, for example, this heat map of, it's going all across industries and also at your home, right? For example, in healthcare and oil and gas, in a pipeline, you're monitoring your air pressure, your oil pressure, your temperature, and if you want to know if there's a leakage or not and where the leakage is, right? And what the viscosity of the oil is it flowing properly or not, or maybe somebody's trying to, tap into electrical wire to steal something. So there's different sensors. So I think IoT has a lot of applications in different spectrum. And this, if I have to tell, for example, my son is in second year engineering and he wants to know what to study, I'm telling him, go into IoT security and you're guaranteed a job for next 40 years after that, because, there is no end to the attack surface and the threat models that exist in this area, right?
Wow.
It's a hugely growing area. And I'm on the next slide, Professor Bhatt, saying IoT use cases. So this is starting from things like
I'm with you.
ADAS or automatic driving. So think of a car as a data center on wheels, right? It is literally generating, 5 petabytes of data every day, because you have cameras, right? You have cameras looking in the back, the side view mirror, the front mirror, everywhere, right? And they are recording, and depending on, are they 1080p or 720p recording, all this data is being analyzed. And in the night when you park the car, the car could exchange data with some other server at your home or back in the Tesla's office to learn from it on what mistakes were made, because the software is still, not foolproof, right? Few accidents have happened, and unfortunately few people lost their lives. And one of the first one was in Florida, where, a steel clear tanker had pulled up and the sky was reflecting, and the camera was fooled to think that it is looking at horizon or the clear blue clouds, but it was a reflection of cloud, and it drove into the truck, and the guy died, right? So I think it will be a while before cars are truly autonomous driving, but they are getting a lot of data on the fuel, the mileage, the economy, and the obstacles on the road, etc. On consumer, many of us have fitness devices to make sure we are walking 10,000 steps a day, we are sleeping properly, and getting exercise and things like that, right? And all the logistics. Someone was today telling me that they are trying to put end-to-end tracking with the berries and the fish, where it is formed, and they're using blockchain for that, and making sure goods are traveling and in your supply chain for your server, where the parts are coming from, and is there, somebody did they change anything on these goods on the way. And similarly with environmental monitoring, IBM did a big project in Hudson River in New York, where they put sensors to see if people are throwing some sewage or chemicals in the water. And in the flowing water, they're looking at opacity by shining some light with a sensor to see how many particles are there, and at which point in the river the pollution jumped up, so they can see at what time somebody threw garbage in, and maybe some other cameras can track that person. So there is no end to, even in smart home, etc. So there's no end to application, but with each application you also think of how someone can hack into it, right? And with Professor Bhatt, I'm working on, a paper beyond this book on the trust models, on how do you assign a number to the security of IoT stack. So the security issues in edge computing, that's my next slide. So number one thing is identity authentication, right? So when you put a lot of intelligence in the edge, so one of your devices can get compromised, and someone can use that device to launch an attack back on you. So for example, if there's a camera, and the camera is feeding data back into the server, but if I hack into the IP address of your camera, then I can inundate your central server with a lot of images. And they call it a Mirabotnet attack, and that was actually launched where they went into a lot of homes where people have surveillance cameras, and people did not change their default password. So somebody hijacked, hundreds of these cameras, and then they crashed somebody's website by sending a lot of images. So from a server point of view, how do you know the person who is sending information, who that is, and what the identity is? And even at your home, if somebody is trying to enter, for example, now Amazon can put the package inside your home in US with some sort of a code that you give them, so people cannot steal the package left outside. But how do you know that it's an Amazon driver and not some thief trying to get in, right? Unauthorized access. So person who is trying to access this either remotely or in person, is that person authorized? And even if they are authorized, are they authorized to go into that particular parameter? Like in an airport, a lot of people are authorized. A pilot is authorized to go into the cockpit, but he or she is not authorized to go into the luggage area. And the guy who is luggage handling is not authorized to go into the pilot area or the cockpit. So you have these rings of security or perimeter of security. So what is the level of authorization you have? So we all know about denial of service attack, and there are different forms of it. There's a distributed denial of service. Then there is DDoS. There's another attack called PDoS, permanent denial of service. So, for example, on a server, if I change the firmware, it will become like a brick. It won't even boot. So you're all familiar with data theft that happened, in a sense with Facebook data, right, where you gave an application some access, and you said yes without reading what all access it wants. Not only it took your data, it took your friend's data also, because in theory you can see your friend's data on where they live or what they are doing, so it used your access to get their data also. Data integrity and falsification. So what I wanted to talk here was, for example, let's say Intel decides to run its job in a VM in a public cloud, and Intel's competition, AMD, also runs a job, right? And some of these jobs land up on the same machine using virtualization holes or using DMA kind of attack where you can cross a VM boundary. They're called virtualization holes. If you can override the other VM space, either in the memory or on the disk, you may not be able to read the Intel data, but you can corrupt Intel data, right? If you can change something in the database, in a design database, you will not detect that error for a long time, and your chip may not work when it comes back. So data integrity is very, very important. And, invasion of privacy. So again, there's a GDPR and big concerns about that. And I'm just looking at the watch. I'll tell you a little story. Google lost a lawsuit in London. So there was some fellow, he was cheating on his wife, right? And he had promised not to do that. But his wife later on was looking up the images using the street map, and she saw her husband walk out of the house of her friend. And she confronted him with this. And he admitted. So the guy got divorced, right? Because he should not have been there. But he sued Google. And guess what? He won the case. Right? So even though what he did was not right, and it cost him his marriage, but he still won the case against Google because, and as a result now, Google has something called right to forget. So, and in the street images, they can take the picture of the buildings or streets or roads, but if they see a car parked there, they have to blank out the license plate. If they see a person walking out, they have to blank out his or her face. Right? So these are the restrictions companies have now because of this issue of invasion of privacy. And activity monitoring, we are all familiar with that, right? So when people leave their child in a daycare or at your home with a nanny, then you want to make sure that child is not being mistreated, right? So it's very simple, right? And also in IoT, you look for any abnormal activity, right? So you look for network packets, you know what the normal is, and when something is abnormal, that means an attack is happening. So I'm on a slide called Security Solutions in Edge Computing. So we talked about the problems. So we have this concept of TCB or Trusted Compute Boundary. Ideally, you want it to be very small, as small as possible. So for example, today when I place my data in Amazon, I am trusting their system admin, right? The person who has physical access to the server or who has physical access to the machine or the root access even remotely, I'm trusting that they will not do something nefarious with the data. But for example, Intel has a new technology called SGX, where the admin or the ring 0 is taken out of TCB, right? So even the system admin cannot get access to your data because the data is encrypted. So data is encrypted not only in the disk, but it's also encrypted at runtime in the memory. With SGX technology, anything that comes out of CPU package is automatically encrypted. Sorry, is there a question? Oh, okay. So the kind of things we have to do in edge computing, that means when you take the computing to the edge devices, so we have to monitor the threat. And the threat may not be just external, that someone has compromised your device. And you have to identify the attackers, and you have to also recover from that attack. And the recovery may be to isolate a device which is infected, so you have some overlap zones. For example, with my security cameras at home, I do not have a single point of failure. After that robbery, I set up cameras in different places, and even if one camera is down or compromised somehow, I can still use the other 2 or 3 to get this picture together, what's going on. And then I have 2-layer system, right? I have an alarm from one company and a camera system from another company. So if somebody hacks into it or cuts it, I still get the images of, whosoever came. But I learned it the hard way. And then there are accidental and unintentional failures which are confused with security attacks, right? So sometime, for example, somebody is trying to get in and they don't have a key, so they jump the fence to get in the house. So it may trigger an alarm and police may come. So you have to make sure that, you have another way to identify that the person is a friend or foe. And, in a home security, it's easy to do, right? You have a database of images, and you make sure that the person who is doing this is a known person or unknown person. I think this is my last slide. So there's a lot of work needs to be done. And number one problem, as Professor Bhatt said, in SOA, the benefit we got was the interoperability between the layers, right? You could switch your database layer without changing your business logic or presentation layer, right? So you could migrate from one to another or change the versions because they are loosely coupled and there are well-defined interfaces between the layers. Unfortunately, in IoT devices today, for their communication, for their security protocols, data storage, there is no such, well-accepted standard yet, right? So today, when I buy a camera system from a company called Zomodo, I have to buy their disk drive and their cameras to store the images, and I have to use their cloud. I'm locked in that sense, right? I cannot mix things. And ideally, at different layers of architecture, right, in a camera with the sensors, optical sensors versus my storage device, these are different layers. So I should not have to go with the same company. I should be able to do mix and match. And there should be well-defined protocols. So that work is still going on by IETF. And what will happen is that over time, some things will happen where either some company will go bankrupt or there will be some lawsuits. This is how standards evolve, right? And then organizations like IEEE or NIST will step in and then they will define the standards. And then folks will start to adopt protocols equivalent of what happened with TCP/IP on the internet traffic. And there are, of course, regulatory and policy issues, and these are very, very complex. Sometimes you don't know who owned the data. So an example is, Intel did this CCC, Cancer Collaborative Cloud, where you had 3 parties. You had hospitals with data of patients which were anonymized. You had medical researchers, who were looking for new drugs for cancer. And then you had pharmaceutical companies which wanted to do drug trials on the patients, right? So no party trusted the other. So they created this CCC cloud where all 3 parties came, and they call it a multi-party analytics, where each party got some piece of the puzzle, either the patient data or the drug data or some new algorithms for solving the problems. And they all worked together, but they could only take the results back. They could not take the data which belongs to somebody else out. So those things are still, regulations or policy are still evolving. And the last one is device data storage across geos and leakage liability. So, for example, Google with Gmail, when I'm traveling to India, they sense that, and over time they replicate my data to their servers in India, so it's faster and easier for me to access. But then who owns the data, right? If there's a court in India which orders Google to surrender that, today they will do that, right? I don't have a privacy. So, and I'm sure somewhere I signed it off, right? Because their botnets also look at my data to serve me ads. But if you're a private company with your data across different geos, you have to follow the local laws. And so what are your liabilities there if your data is compromised? So I think we are in the infancy stage, and the work in IoT cloud is just starting to happen now.
Okay.
So we are almost out of time, and this was my last slide. So, Professor Bhatt, would you like to add anything here?
Well, maybe we should probably respond to any questions that there might be, because we have hardly about 6 or 7 minutes left. So let there be audience participation with some possible queries or questions.
Yeah, so Sharmila, on your end, are there any questions in the room?
Yeah, I think there was one question about the patching, how they handle. Yeah, go ahead, Girish.
So how are they making sure that services are available when the machines are taken for maintenance or patching?
Yeah. That's a very good question. So today they do it very poorly. So when I went to visit AWS, I asked them, do you use equivalent of a vMotion, which is a live virtual machine migration? And the answer was no. So today what they do is, if you are renting a virtual server from Amazon, you get a notice, maybe a 1 or 2 or 3 day notice saying that on Sunday your machine will be taken down for an OS patch or for regular maintenance or routine maintenance, and they will ask you to save your work, so they do checkpointing, and you have a brief interruption in your job. So they essentially are doing stop and restart, and the restart is happening mostly on a different machine than you were on. Right?
That's interesting.
So in Amazon, a server is generally rebooted once every few months, and sometimes 6 months, sometimes even after 1 year. But when it does happen, you have an interruption of service, right? Now, Google, when they did the patch for Spectre and Meltdown, there is a very nice paper. If somebody wants it, send me an email, which explains how they were able to do that on running machines. So they were able to change the bits. So sometimes they can, sometimes they can't. But the solution is very obvious, right? So you take a VM which is running, and you create a replica of that VM in memory on an identical machine, and you migrate that VM, right?
Okay.
So your disruption will be minimal. So first you will copy all the OS bits, all the software bits, and the last you copy the live data. Because in any application, 99% data is not changing. Right now, if you have 3 or 4 gig memory, even in Outlook, you're not changing the data. You're only typing an email or doing some small, looking at something. So most of the things are read-only in cloud. So that's migration is easy to do, but people are not doing that today.
Very cool. Okay. Any questions? Any questions on the bridge? Anything from China or Penang?
Yeah, I have one question. Yeah. So do you have any heat map to show what are the infrastructure data center located? For example, this is showing the IoT opportunities. I want to know if there's something showing about the data centers, to support this AWS. Maybe,
Yeah, I see. So, actually they take pride, the whole idea of cloud is that you don't know where it is, right? So the analogy, the word cloud comes from that it's in the air, right? It's somewhere in the vapor or ether. So actually you don't know where your data is. So when I'm doing my Facebook and I'm uploading my video and pictures, so I really do not know whether, it's in Mountain View or it is somewhere in Seattle. And a lot of these data centers are located close to power station, hydro power station, because the power is cheaper, because the electrical company don't have to do transmission cost. So you don't know. In a private cloud, you would know, right? So in NetBatch, when you submit your jobs, you choose, a particular data center, but you don't know which server.
Yeah, but, I'm thinking how this will relate it to the performance. Since you mentioned the performance is uncertain. Some is due to for the server side, some may be due to the network side, right?
Yeah, so performance will be slow. So what I heard what Google does is that in the daytime, both in Google and eBay, people in US are doing a lot of searches and buying a lot of buying things. So their servers are busy. But in the night when people sleep here in US, their servers are less busy, right? Nobody is searching for a coffee shop in the night here. So in order to keep the utilization to 95, 98%, they route the traffic from Bangalore and other countries where the daytime is there to Mountain View in Google to run the jobs here. So, of course, the service is slower, but their goal is to keep their servers busy, right, 24/7. And the other thing people do is, see, this whole thing is about job scheduling. The other thing people do is, within companies, the jobs which are less important, they will run at night time or weekend. maybe some accounting job, and jobs which are more mission critical, like if you have a chip tape out happening, you run during daytime. And AWS, the way it manages it, it does something called spot pricing, that they will drop the price because the pricing curves are elastic. So they're computing on sales. They will say that for next few hours in their Virginia data center, the cost of 1 hour of CPU is only 0.5 cents, half cent. So a lot of people will rush to get that. And they are doing exactly what airlines is doing, right? So you price the ticket cheaper to fill your plane, or when you have sold more seats, then you raise the price. So this is how but the focus is on utilization today. I would almost say they don't really care about performance. That's the case.
Mm-hmm. Okay, thanks. Yeah.
Really appreciate. I think we're almost out of time. It must be pretty late for you also. Really thanks to both of you. Yeah, Naresh and Dr. Bhatt. Really appreciate your very valuable and very informative session. I think people here really enjoyed it. I'm really thankful to.
Thank you for the opportunity and have fun.
Thank you.
You guys can reach out by email. Yeah. Thank you, everyone. Bye.
Yeah.
Have a good day.
Yeah.
Bye.
Thank you. Yeah.
Thank you. Bye.
Thanks.
Bye.